Now, what we'd really like to show is if this rule holds, then we have what we call a power function, a function that could be expressed as y equals a times x to the p, where p is some power. This is what we mean by a power function if we define it algebraically. Now, we can declare that, okay, well, that's the usual definition of the power function, but I want to use this characteristic as my definition of the power function. And it makes a certain amount of sense to do that, since we see how to construct these graphs. And if we practice constructing these graphs a little bit, we get a natural way of constructing the graphs, obviously with practice, and we get some idea of the variety of graphs that can arise. And there's not a whole lot of variety. Some of them curve a little more than others, but it's either like this, or like this, or like this, or in the one special case, the straight line. Okay, well, we're not going to actually prove that this condition, doubling x causes y to change by a constant factor, guarantees, is a complete characterization of power functions, okay? That's a little bit of a difficult argument, and we'll probably do it later. We're not going to do it right now. But we are going to do this. If we have a power function, that is, if y is a function of the form a times x to the p, then it follows that doubling x changes y by a constant factor, and that factor is just 2 raised to the p power. Okay, 2 for the doubling, p power, matching the power of the function. And it's really easy to see this. We simply say, okay, if this is the case, then, and this symbol means if whatever comes before it, then whatever comes after it. So if y equals ax to the p, then if we let y2 equal ax2 to the p, y1 equal ax1 to the p, follows that y2 divided by y1 is, well, ax2 to the p divided by y1's ax1 to the p. Okay, just substituting these expressions for y2 and y1. Well, then the a's divide out. A divided by a is 1. 1 times this is just this. And we have x2 to the p over x1 to the p, which is just x2 over x1, quantity raised to the p power. So that if x2 over x1 happens to equal 2, then y2 over y1, being equal to x2 over x1 to the p, is equal to 2 to the p. And that means then that doubling x changes y by the factor 2 to the p. Not a particularly difficult algebraic argument, maybe a little more sophisticated than the ones you've seen up to this point, but not that difficult, and one that's definitely worth being able to reproduce and to understand. There's another way to say the same thing using function notation, and it's actually a little more compact. We'll talk about that in a minute. Now I'll say that the converse of this argument, remember this argument says if y equals ax to the p, then the graph has this characteristic. Okay, this characteristic that we've seen here. The converse of that is if the graph has that characteristic, then this thing is a power function. That's a little more difficult to argue, but not that much more difficult. Okay, now there are advantages to this picture. One advantage to this picture is you never put a number on anything. The only number that occurs is this approximate factor that we're using, 1.3 or 0.7 or 2, whatever it happens to be. And I kind of leave that for further discussion, how we determine those factors and so forth, just related to this. Okay, but you never had to mess around with numbers, and there's a good reason that we don't want to mess around with numbers. The reason being that if you're a typical student at the stage where you want to begin to look at power functions, you've had a calculator in your hand since you were a young age, and you probably reach for the calculator to add 5 and 7. Okay? I see it again and again. Talented, gifted students reaching for the calculator to do simple arithmetic that they could more quickly and more reliably do in their head. They don't have to worry about punching the wrong button. Okay? And there's a lack of number sense in almost all students coming out of primary and secondary education. today, and even coming out of colleges, because colleges don't bother to teach it since it's not been taught where it would hopefully have been taught. Okay? So everything done here is just done by geometry, except maybe estimating these ratios, and that's something we want to have a little preparation in doing, but it's not particularly difficult. And there are a couple of other things. There's the idea of what we call proportionality. And I'm not going to talk about that now. We'll talk about that when it comes up. The idea of asymptotes that I referred to here, very difficult for people to understand asymptotes because they don't really understand what division by a small number means, or large numbers. Don't really completely understand the whole idea of multiplication and division. Again, because it's all done with buttons rather than the head. And we never invoke our understanding of what these things mean. The scaling of the graph, well, we're going to talk about that, okay? That's a very important idea. So the reason I like this approach is it doesn't require number sense, but it can be used to build number sense through the process of scaling and other things. And it doesn't require the calculator, which has given us a whole generation of students through the misuse of the calculator who have big holes in their understanding of the universe. We're trying to correct that. Okay, just quickly, the function notation. Well, I'm going to say that, do that on a short subsequent video.